Good morning. Today we're going to talk about skew and kurtosis, two of the descriptive statistics that are available to help us understand our data. So first of all, we are going to invoke two packages, ggplot and simtools. So I'll run the first two lines of code. Again, as in previous videos, I've got some of my own stuff stored in global environment that you can ignore. Okay, and so for this lecture, for this video, I thought it would be easier to just use some completely artificial data as opposed to real health data to illustrate these concepts. And so for skew, I'm just creating a collection of data from 1 through 11. But then I'm using the rep function, rep, in line 4 to create 10 versions of that data. So instead of 11 values, we should have 110 values. And again, if we look at the global environment top right, we see no skew contains 110 values. Okay, if I look at those by typing no skew, we see that I have a repetition of 1 through 11 10 times. Okay, so the rep function works that way. Okay, if I look at the mean of no skew, 6, the median of no skew is 6. And then the skew function, which calculates a statistic based on how much the data is skewed to the left or to the right. And so that means are most of the values below the mean or most of the values above the mean. Obviously, with the median, by definition, half are above and half are below. So the skew can be thought of as a measure of the extent to which the mean is different than the median. Now in this example, the difference is 0, and so the skew should be 0, and in fact it is. And you'll see that the skew function gives us some other statistics, which we will not worry about today, but in a few weeks you will actually know what these other things mean as well. Okay, and obviously we can expect there was no skew here because we created data that were perfectly balanced along a range of 1 to 11. Now, to create data that is positively skewed, this time I have a whole bunch of values that are equal to 1 and a few that are close to the middle, and then one value that is very high. So these data are skewed. So we have more values below the mean and only a few values above the mean. If we look at the mean, we see that it is 6, just like before. But this time the median is only 1. So half the values are below 1, half the values are above 1. So the difference between the mean and the median is high. And so we should expect there to be some positive skew here. And in fact there is. And the skew is 1.769. Now, you may not have seen this notation before, e plus 0, 0, e minus 0, 1. This is called exponential or scientific notation, and some R functions will use it. And so what this does is it says, take the number that appears before the e and multiply it by 10 to the power that is after the e. So in this case, 1.769 times 10 to the 0. 10 to the 0 is 1. So this is just 1.769. However, the SE statistic is 2.335 e to the minus 01. So that's 10 to the minus 1, or 0.1. So SE in this case is equal to 0.2335. And if we look over at P, we see that it's 3.55 e minus 14. So this is 0.000000000, however many zeros, until we get to 14, 35527. So this is a very tiny number. Okay, so that is how scientific notation is expressed in R. Okay, now we move on to negative skew. And so for here, I've done the opposite. I've created a small number of small values of 0, and then a larger number of larger values going up to 10. And again, I've done this to maintain the mean being 6. This time the median should be higher than the mean, and it is at 7. And so we should have negative skew here. And indeed we do. It's negative 0.079. Notice it didn't use scientific notation here. And I believe that is because of, in the previous example, the value of p being 10 to the minus 14th. There's not enough space to put all those zeros, and so it reports all the statistics in scientific notation, whereas with the negative skew, there was room to write all the numbers in the conventional way. Okay, so the positive skew is 1.769, the negative skew is negative 0.798. And you could say, well, does that mean that the second example was more skewed than the third example? The answer is yes. You can compare these statistics to one another. So in fact, the second example was highly positively skewed, while the third example was mildly negative skewed. And actually, as we go forward in the course, we'll be able to do better than saying things like highly or moderately or mildly, because we'll be able to put actual statistics on those, but we're not there yet. Okay, if I plot these skews, okay, and so the first thing I do in line 19 is I convert my previous results into a data frame, and then I use ggplot, data equals skew plot, which I just created, the aesthetic x variable of no skew, and create a geom histogram. Histogram is a type of data presentation that you've probably seen before. So in our first example, we have a perfectly flat histogram, equal numbers of every value, and the skew is 0. And you'll notice in these examples that I didn't do anything with color or labels or legends or anything like that. This is just the minimalist presentation, which I think is sufficient for today. If we plot the if we plot the positive skew, lines 23 and 24, we see that there's a small number of large values and a large number of small values, and that leads to our positive skew. And similarly, negative skew should look like the flip side of this, and it's not as extreme. Remember, we said it was a milder degree of skew, and so we have a small number of low values and a larger number of high values, but not as extreme as the second example. Okay, we move on to kurtosis, which is a measure of the pointiness or flatness of a bell-shaped curve, or alternatively, how much data is contained within the tails versus how much is concentrated in the center. And so for this, I'm going to use a function we haven't seen before called rnorm, and this just generates a random normally distributed value. Normal distribution is what we refer to when we are talking about a bell-shaped curve. And so rnorm will generate a random value with a mean of 0 and a standard deviation of 1. Okay, so if I generate 300 such values, and then I use the kurtosis function to see what the kurtosis is for that result, we see the kurtosis is negative 0.097. So kurtosis of 0 with this function means that the data are a normal bell-shaped curve. So it's not exactly that because I generated some random data, but it's very, very close to 0. If I repeated this experiment many, many times, on the average kurtosis would be 0. Okay, now for negative kurtosis, what I'm doing is I'm generating 100 random values like before, and then I'm generating 100 random values and then adding 3 to those numbers, and then I'm generating 100 values and subtracting 3. So what I'm doing is I am adding and subtracting numbers to push the data into the tails of the distribution. Okay, and so we're going to see this in a graph in just a minute, but for now, let's first verify that we get negative kurtosis from this. And we do, so now we see that kurtosis is negative 1.14. And for positive kurtosis, what I want to do is I want to add more data into the center of the distribution. And so to do that, I create 100 random values with a mean of 0 and standard deviation of 1. And then I create 200 more values where I divide that result by 10. So essentially, I'm making the values even closer to 0 than before. And let's see if that gives us positive kurtosis. And indeed it does. Now it's 4.90. Okay, so I follow the same process as before. First I take my results and convert them into a data frame in line 38. And then first I graph the normal kurtosis. Okay, remember the kurtosis was very close to 0. And we see here we have a bell-shaped curve. It's not a perfect bell-shaped curve, it's noisy, and it's noisy because I only picked 300 random values. If I picked 3 million random values, this would look a lot smoother. In fact, I'll do that at the end, just to illustrate. But for now, all right, so this is pretty close to a normal bell-shaped curve with a little bit of noise to it. And for the negative kurtosis, remember I tried to add more data into the tails. So if we graph that, okay, so now we see something that is flatter, more spread out, if you will, more data in the tails than we had before. And that gave us our negative kurtosis. And finally, when I pushed more data into the center, it gets more pointy or more spiked, and we have positive kurtosis. And again, if we look at the values in our console, these are comparable to one another, and so we had very high excess kurtosis, positive kurtosis in example 3, and milder negative kurtosis in example 2, and that is why example 3, the positive kurtosis, looks more extreme, and this one looks noisier. Okay, so let's rerun normal kurtosis. Instead of generating 300 values, let's change that to 300,000. Hopefully this won't take too long. No, my computer is very fast when it comes to this. Okay, so I can generate 300,000 random numbers and calculate the kurtosis in a fraction of a second. So now we see that the kurtosis is still not 0, but it's much closer to 0. It's essentially 0. If we graph that, okay, we are still, hold on, I have to recalculate the data frame in line 38, and then we graph line 40 and 41. Okay, so this is the data with 300,000 points instead of 300, and you'll see that it is almost a perfect bell-shaped curve. No noisiness whatsoever, perfectly symmetrical. So the more data points you put into these kinds of experiments, the closer you get to the idealized values. Okay, so we're going to end the video there, and thank you for watching.